Hi ladies and gentlemen, welcome to lesson 11. We're going to take a little deeper look at vector spaces, the things that make up vector spaces, and the definition of what a vector space is, and then we're going to focus primarily on the function space made up of polynomials and take a look at some of the things that are inherent with the vector space of polynomials. First things first, we have a little bit of a go back here to make sure that we understand this very important concept. This is a concept, the fact that matrix vector multiplication is really a linear function. We talked about this last time. This is an idea that Strang pushes off until chapter 8 in his text. And so he is saving this generalization, if you will, until later in the course. And we will go through the first couple of sections in chapter 8, but this is such an important idea that we really need to talk about it up front, at least the general idea of what's going on. Again, recommendation that you go look at the Grant Sanderson videos, the 3 Blue 1 Brown videos number 3 and 5, and you can see Sanderson puts this up front in his conversation as well. It's important to understand that what we're talking about with matrix vector multiplication is really a function. It's really a mapping from an input space Rn to an output space Rm, where we have a matrix that size m by n. I'll leave you to read that. The conversation here is largely about dilations and rotations, which are a couple of important linear transformations. They're also easy to visualize. In general, what we're going to do is just briefly take a look at an example of the map.m program. So the map.m program is actually a local in-house program where you can put in a matrix, a 2x2 matrix, and then look to see how it maps input vectors to output vectors. And I'll leave you to read this. There are some specific examples in here that you can look through. This is a conversation about rotations in general. There's one point I want to highlight here, which is just exactly what we talked about last time, where every matrix A is associated with a linear transformation, which I've designated as L subscript A. So every matrix has this linear transformation that's associated with it. The matrices themselves are built based upon the basis functions that we select for the input and output spaces. We'll talk a little bit more about that when we talk about bases, but right now you just need to understand that for every matrix, there is an associated linear transformation, which represents matrix vector multiplication. So specifically here, what I want to do is show you the map.m file. Let me just throw it up here quickly. So this is, like I said, it's a homegrown thing. We haven't changed it since 2018. It works quite well and does a great job of allowing us to build our intuition associated with matrices, 2x2 matrices, and their definition is mapping. So when we run it, we're going to end up with this type of thing right here. This is the default set of values that are in there. What I'm going to do is update the values to make it look like this matrix B. So I'm just going to put this in as a 1, and then this is a 2, and then we have a -2 and a -4. Once we have the 2x2 matrix that we're interested in, we just hit proceed. And the proceed will end up generating this graphic here. And what we can do is we can take a look at how the matrix maps input vectors to output vectors. Under icons here, you can select a variety of inputs. For example, vector mouse allows me to just go and draw a vector, and then the map command is the application of the matrix to this vector. So it is literally the vector that comes as the output of A times the input vector that's here in blue. Every time we hit the map command, it takes the previous output and uses it as the input. This is recursion. So let me just be clear about this. We have A, we've input some vector X, and from that we have another 2x2. In this case, A is just 2x2, so it's mapping R2 to R2. We have an output vector Y. The next time we hit map, it's going to apply A again, but this time to the previous output, and that's going to give us another output. And then if we hit map again, it's going to apply A again, and it just keeps doing this recursively as long as we hit the map command. Let me pull everything back up. All right, so this is our matrix. We've done a little demonstration here. Let me clear this out. I can show you another icon is the standard basis vectors. These are the standard basis vectors we can map. And we can see the mapping is over here. Let's do map one more time. We can see that everything has gone off of our scale. Under map options, you have the ability to change the axis limit. And that will rescale the axes so you can see what's going on. For example, what I'm going to do here is just scale up to 10. And you can see that the standard basis vectors are still here in orange. The first mapping are these kind of light green vectors, and the second mapping are the red vectors. The way the program is set up is it will take, for the standard basis, we have a dashed vector here. The output vector is dashed as well. The j-hat vector is solid, and its output here is solid. So very much like Grant Sanderson was talking about with the transformations, if we look at the basis vectors, we have a very good idea of what the transformation is actually doing. An even better option, one that I prefer to use over the standard basis vectors, let me hit the clear, that will clear out all the picture. I can come in here and select unit square. So the unit square includes the two standard basis vectors along the edges, right? So it's this way, we have the standard basis vectors, but then it also includes an infinite number of vectors on the inside here. And we can kind of see where all of those vectors get mapped. So when we do the map command, what we notice is all of those vectors get mapped onto a line. And then we map again, and we stay on that line. Well, if we take a deeper look, really just a second look, if you will, at this matrix, we knew that was going to happen. What's the column space of this matrix? The column space is the span of the columns, but the columns are linearly dependent, which means there's only one independent vector in the columns, so the column space is the span of 1, -2. And that's exactly what this vector space is. It's the vector space that we go over 1 and we come down 2. It's the vector 1, -2. So all of the outputs from applying this matrix have to go to the vector 1, -2. We don't have any choice. That's the only option there is. And so this again is kind of the understanding and the development of our intuition as to what's actually happening. Let's answer the question here. The question is, find a non-zero vector that is mapped to the origin by our matrix. So what vector gets mapped to the origin by this? Well, we know 0, 0 gets mapped to the origin, of course, but we're looking for something non-zero. So if we think about a vector that we would multiply here, that we would multiply in, we would need 2 copies of the first column and -1 copies of the second column. So any vector, let me clear this, another icon is keyboard input. So the keyboard input allows me to input a vector. I can input the vector 2, -1. So this vector, which shows up in yellow, let me clear and do that again so that you don't have to look at the yellow. All right, here's a kind of red vector. And now if we do the mapping, it gets mapped down to the origin. And then all subsequent vectors are, of course, at the origin. So the answer to the question is a vector that's in the null space of this matrix, a vector that gets mapped down. And in fact, any scalar multiple, all vectors along this line will end up getting mapped down to 0. And we can show that, right? We could pick another multiple here. Let's try -4, 2. Right, so we say, okay, here's our -4, 2 vector. And then when we map it, it got mapped down to the origin again. So this is just a tool for you to play around with. When you hit go away, it will close this graphic. And when you hit quit, it will close the program. Something for you to investigate. There are some options down here to look at to help build your intuition about rotations and dilations. And of course, you can build your own 2x2 and try it out. So vector spaces. We're continuing our conversation today about vector spaces. We already hit this last time. So our emphasis today is a little bit different, but it's a lot of repeat of what we talked about last time. And I think that's important because vector spaces are a general idea that can be difficult to grasp in just one lesson. So what you'll notice in the text here is the emphasis is exactly the same as what Strang has. Vector spaces are a collection of things called vectors, these things that are in a set. So it's a collection of items that satisfy these requirements. These are the 8 properties that Strang lists at the end of section 3.1 in his text. And the collection of items that satisfies all of these properties is called a vector space. As we saw, of course, the vector space always has to include 0, and then we have the definition of closure under vector addition and scalar multiplication exactly as we discussed last time. What I have following here in example 4.11, this example is actually a proof. We don't do proofs, but remember, we can learn a lot by looking at proofs. This is a proof that the vector space R3, that the vectors in R3 form a vector space, so that R3 is a vector space. I walk through each of the 8 properties and then prove that those properties hold when we're talking about vectors from R3. Another important example, in this case it's not a proof, it's only an example, has to do with polynomials, which is really our point of emphasis for today's lesson. And example 4.1.2 shows the application of the properties to polynomials. It's not a proof, but it helps build our faith and intuition that, hey, yeah, the set of polynomials actually is a vector space. We talked last time about the closure. This conversation is about the direct application of those properties. Again, conversations about subspaces defined here, several example problems. If you want to look through those example problems, it will help to build your intuition. And then, of course, the subspace theorem. The subspace theorem says what we said last time. If I have a subset, if I have a collection of things, and that collection of things is closed under scalar multiplication and vector addition, then we have a subspace. And the proof of that is provided here. Proper subspace is exactly what you would think it would be. Obviously, if I take all the vectors in R2, I have a subspace of R2, but that is already the entire space. So a proper subspace is one that is smaller, if you will, smaller in size than the vector space that we took it from. So, for example, the collection of quadratic polynomials is a proper subspace of the collection of cubic polynomials. So the quadratic polynomials are contained inside of the cubic polynomials, but they don't make up all of the cubic polynomials. Another example here, this has to do with the plane. And then here what we have are problems. The problems that are circled in blue are the problems that we're going to do in class. These are the homework problems for this lesson. So we're going to take them directly from the content here. Problem number 2 is a homework problem, except we're going to do that one early because that's one of our participation questions, is number 2. So let's take a look first of all at number 1. It says, and I know it's a little bit hard to read, but it says let our vector space be R squared and W consists of the vectors V that have a 0 in the first component. So we have R2, and then W is equal to the span of everything that has a 0 in the first component. So the second component could be anything. And the question is, do we have a subspace? And what are the 2 questions we have to answer? Well, we know R2 is a vector space. It satisfies the 8 properties. W, in order to be a subspace, has to be closed under scalar multiplication and vector addition. And so we just think about that, right? If we grab 2 vectors from this group, so we grab 0a and 0b, if we add those together, we're going to end up with 0a plus b. Is that sum still in W? And the answer is sure. It's a vector that has a 0 for the first component. Similarly, what if I grab one vector out? I'm going to grab out 0a, and I'm going to multiply by a constant k. That's going to be equal to 0k times a. Is that vector inside of w? And the answer is yes. So w is closed both for vector addition and for scalar multiplication. And because it's closed for both of those things, it's a subspace. So you're going to just use that idea to address these problems in class, except of course number 2 we'll do is the participation question. So the next thing here is section 4.2. We don't have any problems associated with section 4.2. I've included it, I've left it in here if you will, because first of all it talks about a really important subspace for any matrix A, which is the null space. And next lesson we talk about the null space of a matrix A. And it provides this nice graphic. And that's really what I want to do is look at the graphic. Remember, for every matrix A, there is a linear function that does exactly the same thing that multiplication by A will do. Let me grab this out and blow it up. All right, so what we have here is this just pictorial graphic, and Strang has a better graphic that we're going to start using in another week or so. But this does a good job of demonstrating, hey look, the matrix vector multiplication, what we have is a function which is mapping from this side, which is Rn, over to Rm, as long as A is size m by n. So let's write that down. We're thinking of A as m by n. And then the range is the column space. The column space of A, the linear combination of the columns of A, that's the range of the function. The null space is this set of the domain which maps to the 0 vector. That's the definition of null space. So null space is all of the x vectors here that satisfy this equation. All of those vectors are in the null space, and the null space is a subspace of Rn. The column space is, as we talked about last time, a subspace of Rm. It might be all of Rm, but it's definitely a subspace. So there's some information here which kind of relates the whole concept of functions to matrix vector multiplication. You can look through that. There's a little bit more. There's a definition of linear combinations. There's a definition of span. You could review those if you want. But we don't have any specific problems associated with this content. We're going to talk more about it during the next lesson. So what we're really emphasizing here today is polynomials. So section 4.3 has to do with polynomials and polynomial vector spaces. You need to read through this. There are several examples here to help you understand what it is. I'm going to emphasize just one piece, which is vector representation, because this is a really important idea that unfortunately we just take for granted because of the way we've always done vectors. What you don't realize necessarily is when we write down the vector 1, 2, 3, it's actually a set of coefficients. Anytime we write down a vector, it's a set of coefficients. In this case, this is 1 times the vector 1, 0, 0, plus 2 times the vector 0, 1, 0, plus 3 times the vector 0, 0, 1. So this vector represents some vector in three-dimensional space, which we have a pretty good idea of what that looks like. It represents it as its coefficients. What's required for us to represent the vector as a set of coefficients is a basis. We have to have a basis, which in this case is the standard basis. This is just I hat, j hat, and k hat. But what if we had a different basis? As we talked about previously, we can pick any three linearly independent vectors from R3 and we'll have a basis for R3. But how do we represent a vector, a thing that's physically pointing from the origin out to a point in space, as a linear combination of those basis vectors? We need the coefficients. Whatever the coefficients happen to be, that's what goes into our vector. So while we're accustomed to always using the standard basis vectors, that's not always the set of basis vectors that we want to be using. What I want to do is just emphasize this point here with the example. We have the basis 1t, let me move that out of the way, 1t t squared t cubed, and I'll do a different polynomial than the one that's in the book. I'll say r, I don't want to put a vector symbol on it because it's a function, so I'm just going to write down a polynomial here. R of t is equal to 6 plus 7t plus 8t squared plus 9t cubed. If I'm using this basis, then the vector representation for r, which is a list of the coefficients, would be 6, because that's 6 for the basis function 1, 7 for t, 8 for t squared, and 9 for t cubed. And if I had a different basis, I would have a different vector, because the vector is driven by the basis that we've selected. So what would be another basis? Let me just give you a simple example. I'll switch over. I'm going to actually switch this pen back to our green, except the green's gone, so that's fine. I'll use the tan for now. So a set of basis vectors would be something like 1, t plus 1, t squared plus 1, t cubed plus 1. So we could use these functions as a basis for cubic polynomials. If we did, then the function that we have up here would actually have a different representation. Right? Let's think about what that representation would be. I'm going to switch to red because this doesn't show up so well. Let me just erase and rewrite it in red. All right, so what I want is I want the r vector in the red basis. Well, in order to get the correct t cubed, that's going to have to be 9, that's going to have to be 8, that's going to have to be 7. But now I have plus 9, plus 8, plus 7, that's 24, and I need only 6. So how do I get from 24 to 6? Negative 18. So these two both represent the same polynomial, but they're different because they're just vectors of coefficients and I have different bases. That's this conversation here. Following along, you need to read about the linear operator and differentiation and how this works, and then how the output is working. And then, of course, because we're talking about a matrix representation, we know that there's a linear function. There's a function that is represented. We put a polynomial in, we apply the differentiation, we get a polynomial out. It's a function, inputs and outputs. Then there's the concept of inner products. I'll leave you to read about this. This is like dot products. Let me just write down this standard representation that we use, -1 to 1, where we have two functions that we're going to multiply together, dx. This is the inner product of the functions p and q. And inner product notation differs based upon textbook. I'm using the greater than and less than symbols, but you'll see it in a lot of different ways. But the whole point of this inner product is it's really similar to a dot product. Think about what a dot product between a vector and b vector is. It's the first component of each of those vectors multiplied together, plus the second components multiplied together, plus the third components multiplied together, plus however many components I have in my two vectors. Add them all together. Think about what's happening here. For every x, I'm taking the two functions at that spot and multiplying them together. So for every x value, I'm generating one of these. I'm generating a px times qx. And that's happening for each x value between -1 and 1. And then what are we doing? We're integrating, but integration is just the summation. And so we're just adding all of these up. Except we're adding an infinite number of values, and that's why we're integrating. An example is provided here to let you know how this works, and then some more discussion about the representation of polynomials as their coefficient vectors, and then the same types of ideas that we've used earlier in determining what polynomials are linearly independent from one another. Finally, what we have down here are the homework problems. We will complete all of these in class except number 4, and that is one of our problems for participation. So the participation problems are right here. They're all from the textbook. So the text has, from the excerpt that I've given you, 3-2 number 6, 4-1 number 2, and 4-3 number 4. These two are homework problems, so you're getting a little bit ahead with homework there. And then this one is not an assigned homework problem, but it's an excellent thought problem about the whole mapping idea. All right, play around with the map.m program if you want to, and we look forward to seeing you in class. Thanks.